worldwide. In fact, cardiac MRI can be used to diagnose cardiovascular disease in a number of different etiologies, and it can be definitively diagnostic up to 55% of the time with an additional 30% incremental diagnostic value. Even when other workup has been performed, such as echocardiography, cardiac MRI can add a 45% change in management, so it can be useful in that setting as well. Well, what is the gold standard for cardiac MRI, specifically when it comes to measuring cardiac volume and function? And that would be the breath-held EKG-gated SINE, where the patient holds their breath for up to 10 seconds, and a 2-lead MRI-compatible EKG is then used to trigger MR acquisition for that patient based on their heart rate. How does that work exactly? Is that the R peak of the EKG is used to trigger a multi-phase acquisition in which the spatial frequency map of the structure, in this case the heart, is filled at each phase of the cardiac cycle. Through multiple heartbeats, the phases are subsequently filled, and as you can tell here, each phase is being stitched together from multiple heartbeats. So these spatial frequency maps aren't coming from one specific heartbeat itself, but from multiple different heartbeats. Thereafter, mathematical interpretation can be used to change these spatial frequency maps into the MR image that we're used to. So what does that look like? Here's good breath hold, good EKG gating SINE. And for all of these images, I'm using the steady state pre-procession pulse sequence for bright blood to show the difference between myocardium and the volume of blood. Here's what poor breath holding would look like. This is when a patient is not able to hold their breath. And here's when the ECG itself is misfiring or the leads are misplaced. Oh wait, there's more. You could have pathological changes to the EKG, such as fibrillations or arrhythmias, that also distorts the image. And additionally, the MR magnetic field itself can attenuate the R peak of the EKG. And here's what that would look like. So what are some of the solutions? Well, one, Melina will go over, that would be to fix the EKG gating. 2 would be to speed up the whole process of reconstruction. Or 3, in this case, we're proposing the use of a different MRI modality that doesn't depend on the EKG. For example, the real-time MRI. The real-time MRI is a single phase acquisition where the entire spatial frequency map is acquired at that one position, and then the image is subsequently constructed. So this means that the subsequent cardiac cycles don't affect the previous phase of the heart that was imaged. And each phase image is time resolved on its own. Well, what's the problem with this? This sounds great. We don't have the EKG. Since it's a real-time MRI, we don't have the information of what specific phase of the heart we have imaged. So that has to be done manually by either a radiologist or a cardiologist, and that is very time-consuming. Herein, we can use deep learning to phase label these real-time data sets. So here are 3 slices of a real-time data set. We can use a deep learning network, for example, to see exactly where the end diastolic phase is. And once we figure out where that phase is, we can stack those volumes to create a pseudo-SINE. And for that, we can then use automated measurements such as ARDRIS here that can allow us to see the volume and the function of the heart using the stack that we've created. How do we go about doing this? Well, how we did it was we used 241 patients with short-axis SINE SSFP. And the reason why we use SINE SSFP is in deep learning networks, you have to provide annotated information to the model for it to learn from. It would have taken a long time for a person to annotate real-time data. The SINE data has labeled cardiac phases, as I noted, based on the EKG, so we were able to leverage that information. In this case, we had 20 cardiac phases in each data set, as well as temporal steps of 37 milliseconds. We downsampled this because real-time data has a lower spatial resolution, so we decreased the spatial resolution of the SINE that we were using for training, and we did that using a method that is described in the literature by manipulating this spatial frequency map. Then we downsampled it temporally as well by taking each adjacent frame and interpolating 10 times between those. This would allow us to create multiple heartbeats from one heartbeat by subsampling from this interpolated data set. In order to add the label to that interpolated data set, we convolved the end-diastole label by a Gaussian convolution to distribute that information to the newly created frames temporally. And this also allowed us to train a deep learning network that was traditionally built for classification, such as the exception network, to be able to this time perform a regression task, where it's instead of identifying large or small diameter, it can tell you more closely what the diameter is as it's regressing. In this case, we were inputting 3 successive images, and it would give a probability estimate in 2-channel output of end-diastole and end-systole for each of those images that were provided. This then allowed us to be able to identify end-diastole and end-systole. Here, I'm only showing end-diastole for all of these figures, but we have similar results for end-systole as well. So looking at the synthetic test set, running our model on the same downsample Cine data, you can see that the accuracy is 0.91, and the recall, which is similar to sensitivity in clinical terms, is fairly high as well. However, in a real-time data set, these are 11 patients that had actual real-time data. We can see that our recall sensitivity is 100%. So there are no false negatives. However, we do get a decrease in the accuracy. We are getting some false positive predicted by the model. It's predicting too many, for example, end-diastoles. And this problem mitigates a lot once we allow 1 frame leniency. So instead of the exact end-diastole, 1 frame to the left or right of it. Here's what that would look like. Here are 3 slices, again, of a real-time data set. If you zoom in, each slice has multiple frames in it. These slices were annotated by myself and another physician scientist in training, who is now a resident in radiology, and these were correlated with the EKG. Then we ran our model to predict, and we saw that the predictions matched up fairly well. And so this is like a good case example. All right, now that we have this, now that we are able to identify the end-diastole and end-systole, let's create these volume stacks and compare them to Cine data. Here's what that would look like. We see very good correlation between the volume stacks that we created with the real-time data and the volume from the Cine of those 11 patients. And per patient breakdown shows that there is a systematic, here the box plots are the real-time data and the dots are the Cine data. There's a systematic underestimation of the end-diastolic volume and a systematic overestimation of the end-systolic volume per patient. And that makes sense because, as I mentioned, real-time data has a lower temporal resolution, so you're not necessarily always grabbing the exact end-diastole or the end-systole slice. You may be getting a little bit before it or a little bit after it. So physically, that makes sense. Deep learning algorithms can infer cardiac phase, and I didn't talk about here, but we also looked at slice location, and this can enable us to perform volumetry and functional analysis similar to Cine. This is extremely clinically relevant for patients who have arrhythmias or who cannot breath hold and cannot then therefore be a candidate for a traditional Cine SSFP scan. I'd like to thank my co-authors and thank you for your time.
Amin, I thought that was a really cool presentation, very excellent work. I might have missed it, but or maybe I'm being too simple about this, but I'm just curious, could you actually, as a step 1, but maybe you did this, could you just segment the ventricle on every one of these images and then just say, okay, the smallest ones are going to be end-systole and the largest ones will be end-diastole? So in other words, using some prior information, but maybe you did that, or is my suggestion silly? I was just curious what you thought about that.
That's a fantastic suggestion, and actually, if you look into the literature, there's few people who have attempted this, 4 people, actually, and that is one of the methods. What that does is it fails specifically at the basal and apical slices. So it gives a global metric for end-diastole and end-systole, as you mentioned, by looking at the overall volume. But per slice-based specificity is lost in that scenario. So, great question. Yeah. What? Yeah, it's on orders. I'd have to log in and pull it up. Okay. Okay. So for those of you attending RSNA, I will add that so you're not too evil. No, yeah, your picture's gonna go right here. Thank you so much.
That's quite good for a second year.